Welcome back, everybody. It is another great day, and it is another great episode of Everything is a Spring. Derek, how are you, buddy?
Hey, Jim. Long time no see, bud.
Yeah, it's been a minute. So, sorry, everybody, for the trouble that we've had and delay. Recording life is a bear, I think, to say the least.
Right. One day we can make this our full-time jobs, and then we won't have to worry about it.
That would be slick. But yeah, so on my end, it's just been like trying to get the business squared away, and then also, my little sister just got married this past weekend, so that was super exciting. So that was great. She's marrying a great guy. The wedding was wonderful, but also, I'm the big brother. I got to help out, so I was working on that all weekend. So it was really fun and wonderful, but not something that I can miss. So.
Oh, of course. Also, Jim, when do you sleep?
I don't sleep very much. That's just what happens.
Yeah. It's been a busy couple weeks over here as well, but I mean, we're dialed in. Some good news though, I think we should address. We got our first shout out from a pretty popular podcast.
Yeah, I know. I remember you telling me about that. It was the murder mystery podcast or something like that?
Yeah, My Favorite Murder. It's a very famous true crime podcast. It stars Karen Kilgariff. I only know her from the podcast because one of my favorite podcasts, The Dollop, has her as a guest. So I, started looking at her comedy and stuff. Really funny folks. Really great show. And they used us as a source for episode 425 of My Favorite Murder and gave us a shout out, which I thought was
awesome.
Really nice of them. They could have just stole the video and not said anything, but they actually we're forever in their sources link, which is really cool.
That is pretty cool. And welcome all those ladies who are now listening to us because of that podcast.
Right. Yeah. A lot of, we could tell that some of their probably target audience came to us because for the last 60 days or so on our analytics, we're usually about 50-50 split women and men. But this week it was 70% women. So welcome all the true crime fans. Just so you know, this is a data-driven decision. We're not saying that women just like true crime. I like it too. And now I follow My Favorite Murder because it's actually a really well put together show. It's an easy listen.
Absolutely. So that means we really definitely can't go after Big Swift.
If you go after Big Swift now, it's a death sentence. You'd be better off whistleblowing against Boeing. You're not going to survive.
In the interest of not whistleblowing on either Big Swift or Big Boeing, let's talk about something that's before Boeing.
Boeing.
Derek, I wanted to talk a little bit this episode about, because I think we're starting our next mini-series kind of on aviation and flight and planes and stuff like this.
Super hype.
So I wanted to spend a few minutes kind of going over, the kind of the very early history of aviation. So Derek, what do you know about the early history of aviation?
Well, apparently, as one of our viewers were so nice enough to tell us in the comments, I got the Wright brothers' first powered flight completely wrong. So I'm going to humble myself and say not that much. I got the bullet points. But, I'm not one of those guys who's going to be on December 13th, 1910. I'm just not going to know the dates and such off the top of my head. So I'd say intermediate knowledge, not professional.
Okay, that's fair. I'm not going to go super in depth with the dates because I'm not actually really interested in the dates. I'm more interested in the progression of technology, right?
Right on. Me too.
So let's just jump into it. So the initial... there's a lot of stuff obviously that happens in the way back where Leonardo da Vinci is making these theoretical flying machine drawings and stuff like that may or may not have worked. And then there's a bunch of monks that are doing stuff because apparently medieval monks were they're just wild. They're just I don't know, I'm going to make a flight suit basically.
Wait, really?
Yeah, there's totally a medieval monk guy. I don't even remember his name because I don't have that tab open because I already have 55 tabs open right now.
Classic engineering.
But there was a German monk, he wasn't German at the time, but he is in the land area that is now modern day Germany. Monk who made his whole deal was making wings that theoretically would help him fly, and they didn't work. But
Oh.
that happened like way back in the 1400s or whatever.
That's kind of wild. And so you mean to tell me that the idea of Aang from Avatar: The Last Airbender having his little, like, he being an airbender has, like, the glider, that's partially based on reality since he was a monk of this tribe? That actually happened?
I don't know if that. Well, it's like a very different kind of monk, right? Because Aang is based on like Buddhist monks, right? And this was like a Christian monk, like because apparently like the Christian monks were just they like brew beer and they like make flying suits and stuff. So anyway, monks
They
are
sound
slept,
rad as
that's all I'm
hell.
saying.
Where are these Christian monks?
But anyways, so the real, what I'm going to consider quote unquote the real history of flight really begins in the 1770s and 1780s in France. And so it's basically like a couple of French, and I'm going to move through some of this really early stuff pretty quickly because that's not actually what I'm interested in right now, but I want to kind of get there. So it originates in France, and there's these, there's a handful of guys who are basically, there's two main ones. I don't remember their names. Jean-Jacques something, probably. And they make hot air balloons, basically.
Oh.
Yeah. And so the hot air balloons are like, apparently the guy sees like somebody drying clothes over a fire and notices that the pockets are like lifting, right? And so he's like, oh, I can use this. And so that like, and that instigates like this whole, like, basically 20 years of development for hot air balloons. And it ends up with like, the culmination of this particular guy's career, which I don't remember his name, but I remember the details of his career phenomenally well. He ends up being like sponsored by Louis the 16th, or is it Louis the 15th? They got his head cut off in the Revolution.
Couldn't tell you. British history is ancient history. We're Americans, baby.
Well, this is France.
Let's go.
This is France. But anyway, I believe it's Louis.
What's the difference?
Okay, this is going to bother me. Hold on.
We just took out every UK and French viewer in one go.
I know, right?
Hey, in our defense, we don't have any French listeners yet.
That's probably true.
And I see now why.
That's because, I'm about to roast them even harder, so don't even worry about it.
Cook them up.
So obviously the French would come up with a mode of flight that would surrender themselves to the whims of the wind.
I see what you did there.
But anyway. So they're developing like hot air balloons, right? And it culminates with these people launching basically, like, I think from Versailles, a hot air balloon and then traveling like 20 miles. And there was a crowd of like 50,000 people who came out to watch, right? Like this is
the hypest thing that's happened in a long time. Like I can't imagine something like, because you have to admit the townspeople had to think, oh, this guy is going to just fall out of the sky, right?
Oh yeah, it's like, let's go watch this idiot like blow himself up or whatever.
He's trying to play God.
Exactly, right? And so it's like this whole thing. And obviously like the creation of these things is hugely expensive. And so it's done, like a lot of it is done with funding from various different governments. But it's really, what's really fascinating to me is that like, the concept is made in like 1780, I believe, is the first fundamentally successful flight of a hot air balloon. And by the 1800s, they were starting to experiment with like, they were called dirigibles, which are basically like miniature airships that actually had like a propeller on them and could move in a direction.
Oh, that's cool.
Right. So like this relatively very rapid advancement, even though it's relegated to like a very small section of like the people of like populace, right? They're still like very expensive. Like they're not really in widespread use, but like the technology is developing relatively quickly.
And it's a spectacle. Like that has to be a sense of power for the country of origin, right? Like, hey, look at this thing that we're definitely going to turn into a weapon in 10 years.
Absolutely. Right. And then like in like, for example, in the Civil War, the United States is using war balloons primarily for scouting, right? But they are still being used, right?
That's huge. If you can see the enemy before they see you, like even if they see the balloon, they don't know your position. That's huge.
Absolutely. Game changer, right? And so this is like when people start to find out about like altitude sickness from flying, right? It's like, oh, you're going up 9,000 feet in a balloon. You're going to have problems, because you're going up in such a short amount of time. And so like, that's what's like starting to happen. So, all right. So fast forward 100 years, basically. The Wright brothers' first flight, I believe, is in 1903, December 17th, 1903. And they're 12 seconds. That's all it gets, right?
Hey, but that's a huge milestone. Like, you're taking pretty much the equivalent of a brick with wings and getting it off
Absolutely.
the ground for the first time. 10 seconds is awesome. 12 seconds better.
But then 2 years later, they are flying for like 40 minutes, right? So the Wright Flyer 1 flies for 12 seconds. The Wright Flyer 3 flies for like 39 minutes and a half or something like this. In like
what's
a
the time
circular
difference?
pattern. Like 40 minutes, basically.
No, the time difference from V1 to V3?
2 years.
Wow.
Yeah, so because the Flyer 3 is 1904 and 1905 was built over that winter. So I want to talk a little bit about kind of the basic like forces involved with flight. Okay.
Ooh, baby.
So Derek, what do you think like the basic forces involved with flight are?
Well, I think the biggest one that people think about is gravity, right?
Yeah, that's a big challenge to flying is gravity.
Then you got wind resistance.
Drag. Yep.
Drag, yeah. Let's see what else. I don't know if this is really a force, but the weight of the aircraft itself and the materials you use becomes more important in fighting gravity.
Yeah, I mean, we're going to lump that in with gravity because the gravity is really just a force. It has to have something to act on. So
I'm not
the
sure
weight.
the technical term, but the the physics involved around an airfoil and how you can have a negative pressure gradient so that, air can be compressed under a wing so you can have lift.
Yes. So lift. Yeah. So lift counteracts gravity. And then you have drag. What counteracts drag?
I guess what you're putting out of the engine, your output.
Thrust. Yes.
Thrust.
So those are the primary forces involved with flight is drag, thrust, gravity, lift. And so, for example, like one of the things that the Wright brothers had actual problems with is controllability, right? So the Flyers 1 and 2 were very difficult to fly, and that's why they didn't fly very long. The Flyer 3 actually crashes like very quickly. They basically like nosedive into the ground because of the lack of control. So what the Wright brothers are figuring out, because there's no computers or simulations, and aerodynamics is an extremely complicated topic, right? Like, we could spend all day just talking about the aerodynamics. But what the Wright brothers have to do, basically, is figure out all of this from scratch through experimentation and also not die.
That's a big part that we don't appreciate now in the world of drones and models. It's like before, you kind of just had to strap in and, be the test pilot.
Exactly. Like, nowadays, like whenever you've got a crazy idea, it's like, okay, we'll test it with an unmanned vehicle.
Right.
Right. Like do a computer test first. You didn't have that back in 1905, right? You had to fly the plane.
Get in the air bucket, Jim. We're going up.
Exactly. And so like one of the Wright brothers is actually injured in the crash of the Wright Brother 3 of the
And
Flyer
that's the
3.
same flight that had the 40-minute flight time?
Yes.
So they got the stand in the air part down pretty well. The landing bit, that's what gets you.
It's what gets yeah. And so the way that you create a stable plane, and this is like something that's actually really still being figured out through the World War I airplanes, right, is like stability. Stability is a huge issue. And really, I mean, even into the modern day, like stability is a huge problem, right? And like, cause you're balancing stability and maneuverability, right? And so one of the things the Wright brothers do, is that they double the size of the elevators and the rudders, which are basically their control surfaces, right? So give themselves more control over the aircraft. They also add some vertical vanes to try to create additional stability. And they widen the undercarriage, which actually creates what's called dihedral in the aircraft. Do you know what dihedral is?
No idea. I thought that was a shape.
So dihedral, when you're talking about aircraft, actually refers to the angle between the wings, right?
Like
so
the angle compared to the body of the aircraft?
Not really the body, but like the other wing, right? So like if you had a flat, like a 0-degree dihedral would be 180 degrees between the center planes of the wings. Does this make sense?
Oh, it's like straight line across the body versus like canted?
Upwards or downwards, right? So not swept. So sweep is how far the
Oh.
wings tilted back. Yeah, so like for example, if you look at a picture of the what's it called? The Corsair, right? Okay, so the Corsair F4U-1 Corsair, right? It actually has what's called a dihedral wing design, which means the wings actually go up and then down, right? Or down then up in this case.
Okay, I'm starting to see what you mean.
But dihedral would be as if the wings only went up, right?
So this is like, you're not talking about swept, you're talking about the actual tilt up and down of,
Correct.
how much they pretty much bend before they bent on purpose.
Yes, to a certain extent. Although they're usually designed to be that way.
Okay.
But anyway, the point of this is that the dihedral wings, what that does is it basically lowers the center of gravity and raises the center of lift, and it creates basically a resistance to rolling of the aircraft, right?
Oh, instead of having it just flat across the plane of the ground, you actually have a little bit of, it almost works as like a parachute for the aircraft.
Yes.
Like
yes.
you can hold more pressure and peel more off the edges so that it stays in one
Absolutely.
place.
And so like if you think about the forces we've described, right? So there's the gravity, drag, lift, and thrust. How you're applying those forces is extremely important, right? Because the stability of an aircraft fundamentally is a function of how those forces interact with each other. Does this make sense?
So like if they're in equilibrium, you have stable flight. If one is a little more off compared to another, it might cause shimmy flight.
Yeah, well, it'll cause the plane to tip up or down or roll or yaw, right?
And then you're relying more on your control surfaces to counteract.
Yeah, and you use your control surfaces to basically affect the thrust, sort of, it can be a combination. It depends on how you're doing it, but you're using your control surfaces basically to affect your drag in order to redirect the airplane, right?
Makes sense.
So you're using those control surfaces to manipulate the different forces that are acting on the plane in order to create movement. But just for stable flight, for example, have you heard of like the term center of gravity?
Yeah.
So the center of gravity is basically like where the force of gravity effectively acts. So even if you have like a really big plane, basically if you were to take a string and balance that plane so that it wasn't tipping in any direction, the point where that string is attached would be the center of gravity.
Okay.
Does this make sense?
Yeah, it makes perfect sense. Like if I were to put a pencil on my finger and balance it, except in more degrees, like you're looking at all the dimensions.
Exactly. Right. So if you've got a pencil like sideways on your finger and you've balanced it so it's not tipping one way or the other, that's the center of gravity of the pencil. At least in the direction that gravity is at. But let's not complicate things. This
But
is
on
already getting
paper,
complicated.
like every plane in stable flight should have a center of gravity that allows it to continue straight without losing or gaining altitude.
Yes. And so what that means is that your center of lift has to be in a similar place as the center of gravity. And generally you actually want it, I believe it's slightly behind the center. I might be wrong about that. You want it slightly in front of the center of gravity because that will then tend to put the nose of the plane upwards just a little bit.
And for plane speak, that's the last thing you want. That's what we call in the aircraft industry a stall.
Yes, but you use your control surfaces to bend. But anyway, but the point is, so there's now a center of lift. So the center of lift is basically the centroid. I'm going to try to avoid getting really technical.
Do it.
If you take all of the lifting area of the aircraft and you find what's called the centroid of that area, which is basically, if you can think about it as an average. That's not exactly what it is, but for our purposes, it'll work. But it's basically like the same thing with the gravity, center of gravity in the pencil. If you were to balance the lift of the airplane on a string being held downwards, that would be the center of lift. The force of the lift has to be at least equal to the force of gravity, or the plane will fall. Right?
Makes sense. Yeah, like Newton's second law.
F equals ma, right? So it would be first law. But anyway, it's okay.
I was thinking about forces, like it has to be an equal force.
Yeah, so equal and opposite. That, so that actually, I mean, it fulfills all the laws, but...
I'd hope so. If it starts breaking the laws of physics, we got a bigger problem.
So excuse me, I've messed up as well. Newton's laws of motions are as follows. A body remains at rest or in motion and constant speed in a straight line, unless it's acted upon by an outside force. 2, at any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalently, the rate at which the body's momentum is changing with time. And then 3, if two bodies exert forces on each other, these forces have the same magnitude but opposite direction. So basically, if you want stable flight, the sum of forces must equal 0. Since lift and gravity operate in different directions, they must be equal to each other for stable flight. So they sum to 0.
Makes sense. The force acting down is gravity. Force acting up is lift. You want to stay flat? Has to be 0.
Exactly. What this means is that if those two forces are separated from each other along the length of the aircraft fuselage, right, it will induce what's called torque, right? So if you, for example, take that pencil that you're balancing on your finger, and then you start to push up on one end of it, obviously it's going to rotate and fall off of your finger. That's a torque, right? So you're lifting up on one end of the pencil would be the equivalent of the effect of a center of lift that is pushed far away from the center of gravity.
Okay, so I'm thinking of it like a sliding scale as you tilt the nose up and down.
Correct. So in the instance of the Wright brothers Flyer 3, presumably the center of lift and the center of gravity were not adequately balanced within the control surface's ability to correct.
Oh.
And that would then create a stall condition or a nosedive condition, depending on how it happened. Right, so then you have the same thing with the center of thrust and the center of drag. Right, so the center of thrust is basically going to be in the middle of whatever engine or propeller you're using. And then the center of drag is going to be determined by the cross-section and the aerodynamic coefficients of the different bodies that make up the plane, right? Generally, your center of drag and your center of thrust aren't as big of a deal as where your center of lift and center of gravity are, but they can create an interesting effect, right? Because if your center of thrust is above your center of drag, that can create an opposite torque to the center of lift, center of gravity torque.
What does that mean?
you can kind of use them to balance each other out, right? Which is probably actually not helpful to our current discussion.
But it is interesting to me. Like when I'm playing flight sim, like one of the ways that very simply to bring your nose down without touching an actual control surface is to lower your power. So it makes sense that these are related in a way.
Yeah.
In multiple ways.
And that can be the result of a number of things, because by lowering your power, you're also basically you're slowing down, because the force of drag is now going to be slowing you down. And that's going to reduce the airflow over your wings, which is going to reduce your thrust, which is then going to reduce the amount of force holding the front of that plane up, because probably your center of gravity is a little bit behind your center of lift. And that's going to cause your nose to tip down. So yeah, that's the physics behind it.
Well, you learned something, viewer. That's how planes work. Don't at us.
So I wanted to talk a little bit more about the Wright Flyer, because it's actually a really interesting plane. One of the things that it lacks is basically like what do they call?
Ailerons?
Ailerons. Thank you. I don't know why I have such a hard time pronouncing it. It's spelled very strangely.
It is.
Ailerons.
And I probably even said it wrong, but no one's corrected me yet, so we'll see.
Fair enough. Anyway, so most modern planes, I would say almost all modern planes, if not all modern planes, use ailerons to control, basically to change the shape of the wing in order to create, if you're going to turn them opposite, you're going to create roll. If you're going to turn them together, you can create pitch change. And then I guess if you really got weird with it, if you rolled and then you pitched, you could create yaw, but that's not really
I
how
wouldn't
they're supposed to
suggest
be
it.
used.
Maybe if you're in a fighter jet, that'd be pretty slick.
That's fair. Anyway, so the point is, your ailerons are used really to create roll and pitch. The Wright brothers did not use ailerons. They actually used what's called wing warping, which is
Wing warping?
which is generally in today's modern planes would be very bad. And so they're actually changing the shape of the wings using pulleys and stuff, basically to pull on the different sections of the wing to create torsion in the wing structure to create roll, right? And then they're doing similar things to create more like up or down. Basically what I'm saying is like the Wright brothers plane was like a paper airplane, basically.
Oh.
And so if you take a paper airplane and you kind of crease the back of the wings up or down, that'll like trim like the flight characteristics of it.
So like this balsa wood plane they've made, they pretty much got it like, it's like a transformer. You're pulling on a freaking rope, and then a little bit more wing gets pulled out of it or something. They don't have any control surfaces besides that.
Yeah, the control surfaces are basically the entire wing, and you control it by flexing it, by just yanking on the thing.
Oh, you're literally just bending it.
Yes.
Oh, I thought it was even more complex than that. It's literally just, you know what, bend it a little bit.
That's pretty much it.
Okay, well, you got to start somewhere. I mean, I don't have any notes because I didn't make the first powered flight, but that has to be way scarier than flying today, right?
Yes. So
you're just actively making your wing bend. What if you snap it? You're done.
And that's what people started running into, right? Because you are actually like structurally flexing the plane, right? Like that's how the plane works if you're doing it with wing warping. Is you are literally bending the structural members of the plane to create change in direction.
Oh, maybe that's where Boeing got their like flight set.
And so one of the things that like they actually get this from is actually birds, right? So birds obviously are organic creatures, right? But they actively change the shape of their wings to create roll and flight and trajectory, right?
Yeah, but birds are cool as hell and have some of the most complex joint and muscle structures of all of their class. Like, you can't just... I guess you could build it out of balsa wood, but... Oh, that's tough. Like, there's the difference. A bird can tuck his wings and bring them back in. You tuck your wings, you're done.
Yeah, so it's very interesting. So... But I think it's cool that it comes from nature, right? Like this is where it initially starts, and then people start figuring out, oh, okay, wing warping is really hard. Let's come up with something that we can achieve with the technology that we have, right?
Right.
And so, and again, like one of the things that's fascinating to me about early aviation is like how fast the technology progresses. Because again, Wright brothers, first powered flight, 1903. By 1911, biplanes exist.
I didn't realize it was that quick of a turnaround, but I guess this is it's like seeing the internet for the first time. I guess that's the closest thing that we can compare it to in our generation.
Yeah.
Because like there's been nothing really new. I know that's probably not true, but from what I've seen, we've seen different versions of stuff. Like there's not been, oh, this is the cell phone, this is the iPhone, this is the iPod. Now it's like, oh, here's the generation 10 of that thing. To see powered flight as a different country for the first time, you had to like, all of your scientists would want to be into it. Even if you're like biologists, you're like you said, sure. You're looking into how do birds fly, like actually looking at the taxonomy. That's really interesting to me. Like, if you to take it a step further, powered flight let's just say early 1900s, 1903 to like 1911, we're going to space in the 50s and 60s, you know?
Oh, yeah. Yeah, like literally, it's wild to me. And I think like the other thing too is like I actually think that like there's a lot of similarities between like the speed of adaptation of aircraft and the speed of adaptation of like the internet, right? Because if you think about like the internet, yes, like it was around in like military installations as a tool for that for a while. But then like it really wasn't until I would really say the 90s that it became like widespread public. And then, you know, here we are 20, 30 years later, and it's like, it's an integral part of our everyday life.
Yeah,
you know?
like before the internet was this thing that stores, you know, probably non-essential data at first, like your contact list, stuff like that, emails when that became a thing. But now I can't think of a company today, besides like brick and mortar shops, that if the internet truly went down, like on a regional level, that company would be able to operate at even 50% capacity.
Yeah, absolutely. And so similarly, I think like you look at planes, because 1903 first flight, and then, you know, by the 1920s, like farmers are using these things.
Yeah, they're crop dusting.
You know, they're crop dusting with them and stuff like this. And so like, to me, like that is such a hugely rapid advance of technology. And I think it's just interesting to see it, because like we hear so much nowadays about like, oh, how fast everything's changing and like the speed of technology is increasing, but like it was fast back then too. I mean, you know, it's like life changes so fast, and I don't think that's a new thing, which is maybe of some comfort in today's wildly chaotic times.
I think the only difference is we changed the acceleration rate, right? Like, if I wanted to build something back in the 1900s, I'm drawing it out. I'm having to get someone to build this specific part that's probably never been made before, right?
Right.
Nowadays, I can email Jim a file. We can 3D print that bad boy, get a powerless model just to see how the balance is, get the weight distributed. Or, alternatively, you could just say scrap the model. Yeah. Just simulate it until you get something good.
Absolutely.
Outstanding.
Yeah, so really fascinating. But so that's one of the things that the Wright brothers flyer, I think, did that was really cool, that ended up getting scrapped quite quickly. But there's actually some interesting, like modern stuff happening with, it's now called adaptive wings, right? It's no longer called really wing warping. But basically, like because the thing is, like the introduction of control surfaces actually creates a lot of drag. Because you can't have those two surfaces be perfectly even, right? Like perfectly smooth at all times, especially in like modern aluminum construction.
Right, there's going to be gaps.
There's going to be gaps, and those gaps create a significant amount of drag. And so if you were able to eliminate those gaps by having a wing that would be able to morph itself, for lack of a better word, to adapt to the changing conditions without having a break in the skin, you would be able to really increase the aerodynamic effectiveness of that wing and reduce drag, which is obviously really excellent for a lot of different reasons.
Were we talking about the F-14?
I don't know. I don't know enough about the F-14. But like NASA's got a project on that going on, and I'm sure DoD does as well. But anyway, this is we're way off topic. I think I've planned this episode quite poorly because I thought I had more time than I did, but it's fine. So what I really wanted to get out of the Wright brothers thing is that there's this idea in early aviation that airplanes should be flexible. Derek, what are your thoughts on flexible aircraft?
I think it makes sense, at least in the wings, right? Because the way I understand it, as not an engineer, if something has some give to it, I don't know what the technical term is for some give to it, but like you can go on any Boeing aircraft recently, especially that Dreamliner, if you're flying that death trap, the wing has 30 inches of sway at the tips. It's designed to, actually allow what used to be a very rigid structure to flap like a bird. And by doing that, it causes less actual effect on the passengers inside. So the wings are getting all of that tear or that wind shear, but the actual body of the aircraft isn't. So I think flexibility in aircrafts is important for them not just, snapping apart.
That is true. I should maybe revise my question, because there is, and again, everything is a spring, including airplanes. And that's ultimately why the wings flex, is because there is a modulus of elasticity to all the components that go into the aircraft wing. It is going to flex to a certain degree, That's just going to happen. So designing for that is very important. But let me, I guess, rephrase my question. In the light of early avionics or early aviation, what is like maybe the problem with flexing structures?
Getting them to come back, like getting it to snap back to its original form.
Yes. And so there were lots of problems in early aircraft where basically like things were flexing too much. And this was not really understood at the time because aerodynamics, again, highly complicated. But what I want to talk about today is a little thing called flutter. And I think we talked about this a little bit because flutter is actually one of the aerodynamic, if you remember back to our Tacoma Narrows Bridge episode. Yeah,
aeroelastic flutter, right?
Aeroelastic flutter is what ultimately caused that bridge to collapse. Well, aerodynamic flutter can actually happen on a lot of different things. And what it's caused by is basically this idea. It's called the Kármán vortex sheet. And so a vortex basically is basically, if you think of air and you're moving through that air, you can think of the air as a linear set of streams, right? So as you introduce objects, it creates turbulence. Depending on the shape of the object, specifically like spheres and long spheres and long flat surfaces that are presented like bluntly to the wind, create what's called Kármán vortices. Kármán vortices are oscillating vortices, right? So first it'll go to one side, like the airstream will go to the one side of the object, and then it'll go to the other side of the object, and then it'll go back to the one side of the object, and it'll create these shedding vortices of oscillating air. And what do you think might be the problem with that, Derek?
Well, I mean, if you're something like an aircraft, experiencing that when your design is not made to shed that off easily, it can completely change the flight dynamics of that body. You could have control surfaces, but it could overpower them. That would be my concern.
That is actually a fair point as well, because the reason that control surfaces work is because they are pushing against the air. And if the air has separated from the airfoil, it will no longer be effective. And that's actually like a whole different failure mode of planes. I'm not sure what it's called, but I guess it's just like when your angle of attack exceeds what the plane is capable of doing. That is what has happened, basically, is that the air is actually separating from the wing before it can hit those control surfaces, and you lose control of the plane.
You know, Jim,
Derek, is there a name for that?
I would call it falling, but I don't really know. What is it called?
I don't know. I was asking you because you do air stuff.
Oh, no, I'm not an aerospace engineer. I had a phone in a friend.
You're an enthusiast, right? So I don't know if that would be called like a flat spin or something. I don't know.
Oh, like when you actually just lose airspeed and straight down?
Well, I don't know. I mean, so like, I guess, let me...
Like, help me understand what you're describing. I can tell you if I know a word for it. Because a flat spin is more like a planed... Yeah, you don't have any forward momentum. You don't have any backwards momentum. You can't adjust the nose up or down, so you're in what they call a flat spin. Your body is literally just falling down the y-axis, not really changing much.
Okay, so maybe like... So if you're moving straight, like the airplane's moving straight ahead, and then you like nose up really fast.
Ooh.
Right. And then like you obviously like the plane's going to want to start like going up. Right.
Right.
What can happen there is how do I explain this? Let's see. Angle of attack separation.
Like, I guess
boundary layer
is it stalling?
What you're talking I guess about? It is stalling. Yeah. Well, it would be, right. Because that basically what that represents is if you're moving, if you pitch up too fast, the airflow is going to separate from the top of the wing, which means you're no longer going to be generating lift from the wing, which means you're going to stall because you're no longer generating lift, and so you're going to fall.
Yeah, like the thrust is now overwhelmed by the amount of drag.
Yes.
All things considered.
And
your airspeed's going to drop significantly.
So I guess like that's the interesting thing is like if you have a high enough thrust to weight ratio, you could actually get out of that by basically just
Throw some power on it.
throw some power on
That's
it.
the whole concept of the F-15 fighter jet. You know, if it's so fast and that we can just put it in space, why not? Shoot a satellite down.
I guess at a certain point, like if you can just travel directly up, you're fine.
Yeah, that's really what it is. It's like if you have the thrust to counteract gravity at that angle, go for it. Send it.
I think I've gotten very far off topic, but it's fine. we might be able to treat this episode as like a little bit of a precursor, like a little bit of a premiere on flight, maybe.
Yeah, it could be like a little, I won't call it mini-sode, but, you know, it's like more flight dynamics, like the fundamentals of flight, right?
Yes.
And a brief history.
A little bit of history. So these are all some of the things that, like, very early aviation folks had to figure out. And again, mostly by trial and error. And so, like, aerodynamic flutter became, like, a big problem. Specifically, if you look at biplanes, you know, what do they have connecting the top and the bottom wing?
The wire? Body of the aircraft? I don't really know, actually.
So a lot of these early biplanes and even the triplanes have basically wooden sticks that connect the top and bottom of the aircraft.
Oh, it's literally just frame? That's it?
I mean, so like here, let me...
I guess that makes sense. I mean, it's 1920. Yeah, just slap some more balsa wood on that bad boy.
So this is a Sopwith Camel, which is, World War I era fighter biplane.
Gorgeous.
But like you can see, they've got basically sticks that support the bottom and top wings together.
Yeah, and then like some wires to kind of stabilize it throughout.
Yes, the wires provide like a lot of torsional resistance, or like basically like triangulation, right? So they help
triangle
create
strong
stability.
shape.
Absolutely. But these sticks that are up and down are basically phenomenal areas where you can create Kármán vortex shedding.
Oh, like individually. That's
yes,
kind of concerning.
Exactly. And so I'm going to send you a picture of the plane that I was going to talk about today. This is Caproni CA48. It's an Italian plane. And they actually used this. This was basically the first, or one of the very first, commercial airliners.
Jim, I don't want to correct you. That's clearly a Combine.
It's a real plane.
There's no way that thing flies. That's ridiculous.
Allegedly, it did. And so these were basically basically a conversion from the Caproni CA-42, which itself was a variant of the Caproni CA-4, which was a heavy bomber employed by the Italians in World War I.
Huh. Heavy is in big quotes compared to what we got today.
That's very true.
But I guess, for this, if you go slap a bomb on this thing, I mean, that is game changing. Look, it's got 3 vertical stabilizers too. Like,
oh yeah. And this was a really interesting plane because it was also basically like a bimaran, right? So that's not what they're actually called. It's called a twin boom aircraft. So basically, it's got like 2 fuselages that are next to each other, and then those are like connected with the wings.
Oh,
and then there's like a center section as well. And this is like a 3 aircraft airplane. So there's basically a pusher airplane engine in the center of it. And then there's 2 puller airplane and like they're called tractors because they attract the air towards you, that are at the front on top of, or on the ends of each of these booms, right? So this is a 3-engine aircraft and it's got 3 wings. It's a triplane.
It is quite pretty.
It is.
Like,
and
the longer I look at it, the more I like it.
And the whole thing is made of wood and cotton.
Hey!
Basically.
How? Wait, why?
Well, because it's fabric covered. It's not really cotton.
Gotcha.
It's basically, the whole thing is made out of sticks and fabric.
Woven cotton, okay.
And it's carrying 23 passengers.
That's pretty big for like a combat aircraft. 23?
Pretty impressive.
That means you lose 23 men every time one of these goes down.
Oh, that was the airline version, not the not the bomber version.
Oh, so they just made two versions of the same thing?
Well, basically, after the war, what are they going to do with all these bombers?
Convert them.
They got to find something to do with them, so they converted them into a lot of different things. But the one in particular we're talking about was converted into like an airliner.
This must have been Bird's worst enemy of the time. Like, this was the apex predator of birds all around the world for a little bit.
Yeah,
look
probably.
at it. It's just it looks like a screen when you look at all of the support wiring. Like,
yeah, I don't think it went very fast, even though it was powered by literally 3 V12 engines, like putting out 400 horsepower each.
we don't even have to LS swap this thing. That's sick.
Yeah, dude, if you want to talk, oh my gosh. Okay. We're going to get on a huge tangent again, but basically like these early airplane engines again are like so advanced, like so much of the technology that exists in modern vehicles, like cars, already existed in 1912.
Which is wild. But if you look at a like expansion
wild.
of a rotary engine, which we've talked about in our last aircraft episode, it is the fact that it works alone is impressive. The fact that they made this on pen and paper with technical drawings is nuts. Like, how do you get all of those pistons to fire correctly? Absolutely. And you don't have a frame of reference. Like, you're figuring this out for the first time, all things considered. I guess you could take a lesson out of steam engines and kind of just adapt that to higher force, but it is impressive what they were able to do with early powered flight.
Oh, for sure.
This thing looks awesome.
And like, again, like we think of like, you know, overhead camshafts. Those weren't like really commonly used until like the 1980s or whatever, or 1990s even maybe.
I didn't realize that was
until they were commonly used. Like push rods were huge for a long time. But like these aircraft engines have dual overhead cams, you know, and like that's why, and they're air cooled. Like, what? You know, that's why they're making this much power, you know. But anyway, it's incredible because in aviation, power to weight is everything, right? Like your power to weight ratio when you're trying to go fly is huge. It's so important. And so like, yeah, in 1910, there's already dual overhead cams in cars, you know, and in planes, and like, it's insanity. Anyway, I get off on a tangent.
This whole podcast,
this is the kind of stuff that's
the
so
alternate name is a tangent.
Oops, all tangent.
Dude, one day.
So anyway, back to the, Caproni. So, what ends up happening is that in 1919, August 2nd, 1919, this Caproni CA-48 is flying from Tagliado, which is in Milan. It flies to Venice, and then on its way back, as it's returning to Tagliado, there are eyewitnesses that report as the airliner was passing the airfield at Verona at an altitude of 3,000 feet, its wings seemed to first flutter and then to collapse entirely.
Oh.
And then it crashed, ultimately leading to the deaths of between 14 and 17 people, depending on who you ask.
And we're still talking about the 3-winged atrocity that the Italians made. Okay.
Yes. And so, like, this is the first, like, airline disaster pretty much recorded in history, which is kind of interesting. But also, this is the first, like, real instance of flutter causing an airliner accident.
And there are actual witnesses for it. So
there are witnesses.
Think about if this just was out of sight of the city, you would have never known. Or it would have been really hard to ascertain how it crashed back in the day.
That's true. That's true. So, you know, the theory that I have on basically what happened is that the wings were really not rigid enough. And so, well, that's not really a great way to say it, because what ultimately happens is the von Karman vortices that are created by all these different structures ultimately create an oscillation in the wings. And that oscillation causes the failure. It causes the aerodynamic flutter, which then causes the structure of the aircraft itself to fail.
So this is why you're asking me about why flexibility is important, but there is a lower limit.
There is a lower limit. There is a certain amount of rigidity that you need in order to basically prevent a positive feedback loop. And again, this goes back to damping, which we talked about. You need to have a well-damped system. So even though like the Boeing aircraft wings of today, they do flex, but they flex in such a way that the damping of that movement will not create a larger and larger oscillation, because that is what leads to failure.
Intentionally.
There is probably active design in the Boeing 737 and all their other aircrafts, and probably most modern aircraft, if not all modern aircraft, to actively have a design that dampens oscillations in the wingtips, but doesn't prohibit it.
So it really is a range of motion that you're like an allowed range.
Yes.
I guess operating range.
An allowed range, but also an allowed rate of return, because that ultimately is what damping is.
Oh, so it doesn't snap back too quick?
Yes, because if it snaps back too quick, what'll happen is it will then go the other way.
And then you change the flight dynamics of the aircraft again.
Exactly, and you put additional stress on the airframe.
You probably snap your wingtip off, because wind don't care about you.
Exactly what happened to this 1919 flight at Verona.
Hey, NTSB, we'll take... I'm not even going to put in a job application. You know where to find us.
So that's kind of like interesting. And one thing like I wanted to kind of bring up in conjunction with that is the Handley Type O, which again is another of these World War I era fighter aircraft, or bomber aircrafts, I suppose. Because this was a strategic bomber used by the Allied powers.
Looks like it's got a sweet speaker system on it. I bet the pilot's bumping right now.
It does.
Probably playing Kendrick.
So the Handley Type O basically went through like several different iterations and prototypes, and the initial designs had massive oscillation problems, specifically in like the rear section of the fuselage, right? And so over the course of 4 different prototypes, basically they had a guy crawl inside the fuselage and look at what was moving around in order to make the design changes that they needed to stiffen the airframe and basically reduce the what you're effectively doing is you're changing the frequency, the resonant frequency of the aircraft by increasing the stiffness of the aircraft.
Okay, so it's still oscillating, just at a lower rate.
Yes, and specifically at a rate that will not create a building, compounding oscillation, right? So we talked this was a while ago now, but we've talked in the past about compounding oscillation, right? So if you think about like waves, like if you're playing in the pool, right?
Right.
And you like push the water, and you've got like against a wall, right? So you have like a wall, and you like push the water against the wall, you create a ripple. As that ripple hits the wall, it bounces back at you. And if you've created another wave, where those 2 wave crests meet, they spike. So they create a bigger wave than either of the waves individually.
Oh, like it's additive.
It's additive. The same can be true with oscillations, right? So when you have, if you look at oscillations over time, right, they create sine waves, basically, which is the same shape as a wave, right, in water, as a waveform. So if those peaks of those oscillations match up, or the force that is applied matches the peak of that wave, it will magnify, it will create a greater amplitude of deflection.
So if you have that powered force keeping going, like in this case for an aircraft and engine, you could actually end up having a feedback loop.
It could be vibrations from the engine. It could be vibrations from aerodynamic stresses like von Karman stress or vortex shedding. It could be a lot of things, but any of these things that create, or you could just be wiggling the stick back and forth, right?
True.
Like you could be
pilot
maneuvering. Error. Could be pilot error as well. But that any of these things can create oscillations that, if they are compounded, in the right way, have a chance of meeting the plane's resonant frequency or the structural resonant frequency of the aircraft, and then magnifying. And that is really what creates a lot of these very fast catastrophic failures that are, indicative of like the 1919 Caproni crash.
It's
like,
interesting,
I guess,
like the same kind, not the same type of force. I don't want to piss off every engineer that listens to this podcast, but the same reaction of force to force, like this cyclic feedback loop, feeding on itself and powering itself to the point of failure, which by eye is unseen. Like you're probably not watching this happen. It's micro until it's not, right? And your wing snaps off.
They could definitely start very small, but like as they get bigger, you will see it.
You're going to feel it.
You're going to feel it. Oh, you're going to feel it. Absolutely. Especially when the wing snaps off. Yeah. So I wanted to bring up, the Handley Page Type O, because ultimately, like, this is one of the first aircraft that is specifically dealing with this issue of oscillation. Especially like in a military context where you really have to have, you really need that stability, right? Because, operational conditions are never ideal.
No. And you're trying to, you're in a flying object, trying to make a object you're about to drop land where you kind of want it to without hitting the village next door.
Exactly.
On paper.
And so, so like literally they spend a lot of time and effort and have a guy literally in the plane watching the structural members flex to make it better, right? And they didn't really know, like they're not really familiar with like vibration and oscillation theory at the time. But like this is some of the foundations to this. And this actually leads to a lot of research in resonance, right? Like the whole, physical study of resonance kind of starts here in World War I.
That is really interesting. I thought resonance started with chemistry.
A different type of resonance, right?
Oh.
But it's the same type of resonance that's like in bridges and stuff. So I guess it doesn't really start in World War I, but like there's a lot more, because like previously, like the resonance we've been talking about really has to do with bridges.
Right, and those are like fixed point. Like bridges do flex, but they are fixed in position.
Yeah, they are like fixed to the ground. An airplane is completely unsupported by anything except for itself, which makes it really unique in terms of like resonant geometry and study, because there's, any damping that you have ultimately has to come from the structure itself. You can't rely on the ground to provide that damping effect.
So, like, is that what those big pods are on either side of the cockpit? Or is that a weapon?
Those might actually be engines.
That's the engine?
Are the engines. I believe those are the engines.
Oh. You'd think you'd kind of want those protected by something, but I guess if it ain't broke. It's literally just supported by like a couple more of those support pylons, what it looks like.
Yep, absolutely. And actually, like one of the things that they did during like development of it was they actually removed some of the armor plating to basically, again, change the resonant frequency of the aircraft.
So it flies great, just don't get shot.
Well, that's like a big thing with most, especially because a lot of these planes are made out of, again, canvas and sticks. So don't get shot. That's good advice.
So like, what does it all boil down to, Jim?
I kind of lost my train of thought at the beginning of the episode. But I think like what we should get out of this episode is basically, flight is dictated by 4 forces, right? It's drag, it's thrust, gravity, and lift. Those are very important. The flight characteristics of an airplane are also very heavily determined by the positions and relative positions to each other of the center of lift, the center of gravity, the center of thrust, and the center of drag. So, for example, like if you look at the really, really early aviation stuff, balloons, your center of lift is well above the center of gravity. And that is what makes them so stable, right? So if your center of lift is above your center of gravity, you're going to have a stable aircraft that doesn't want to roll over like a hot air balloon. But a hot air balloon is not very maneuverable. So then you develop other things.
Yeah, slap some propellers on it. All of a sudden you have a airship, right?
Exactly. And now you're making your lift with wings as opposed to hot air. So now you can do a lot of different things with where your center of lift is and where your center of gravity is in relation to that and how all that interacts. And it is very complicated, but also quite fascinating. And you can do a lot more interesting things with that once you have this changeable relation between the locations in both X, Y, and Z directions of the center of lift and the center of gravity and the center of thrust and the center of drag. Because, like, for example, one of the things that they actually do to reduce the oscillations is they actually offset the tail section of the Handley Page Type O. They actually offset the tail section slightly to one side. And basically what that does is it creates an uneven, because you're generating vortices, it creates an uneven vortex generator, so you have a more consistent break of the wind around the rear of the plane.
Wait, so it being off kilter is actually a positive in this situation?
It can be. And specifically because they had such huge vibration issues or oscillation issues in the tail, offsetting that to one side is going to change how the vortex is shed off the back of it. And so you have now, instead, it's not exactly balanced, but it is consistent.
That's the key. You can adjust everything else that's in your control after that.
Exactly. So it's very interesting. And like, I really recommend like reading up more on the Handley Page Type O, like development period. Even just like the Wikipedia page would be a lot more detail than I've had time to go into here, but it's really fascinating how they basically took, basically it's just all on paper. It's just like the experience of the aircraft designer, which again, remember in 1915, the most experience they could have had was like 10 years.
Listen, I saw the first Wright brothers fly. Listen, get out of my office, damn it.
Exactly. So, not what I would consider like a hugely, bank of experience to which to base a flying object on, basically off just raw gut instinct. But, it is what it is. And
there's something to say there, Jim. Like, gut instinct is the fundamental core of modern flight. Like, obviously we have regulation today, which is good. I want to say on the record, regulation is good and it is written in blood. But, these folks trying to push that next boundary, what if I can do this? That's what got us to the moon from 1903 to 64. Like, it's incredible. Like,
absolutely.
And I appreciate you talking about the time scale, because it's hard to think about. Like, we've been alive 26, 27 years.
Yeah.
Think about how aircraft have changed just since then.
Oh, for sure.
Like Boeing 777 to the new 737s we have today. All of everything Airbus has done to catch up and like actually put Europe on the market as a major aircraft manufacturer. Those are pretty big jumps.
Oh, yeah.
You look at something like the A320, it's one of the biggest aircraft in the world.
Yeah, and that's not even diving into the military stuff.
I can't wait, Jim. But like, I guess for our listener, I know this was kind of, usually we have like a specific object to deal with. This was more like introductory flight and some nerds going on tangents about early days. So that next episode and the episodes after, we can hit you with something a little bit more complex.
Yeah, that's true. And like, I know that this was like a very technical episode, and I hope that doesn't throw people off.
Oh, it's okay. They're all asleep by now. We can start talking trash.
There you go.
I enjoyed it because
anyway.
This is a class I took with Civil Air Patrol. They have a whole book that it's like flight dynamics and all these things. Like, it's teaching you the basics of flight before you can even touch an airplane. And it's interesting how it all kind of clicks once you have the control surfaces at your disposal. Like, the simulator is one thing, but once you can feel the counterforce in your body and like in your ears as you're like adjusting to what's up, what's down, what's left, what's right, it's incredible experience. If anyone has the funding to do so, or if there's a program and you're interested, I would highly recommend trying to go into flight school, even if it's just for an orientation flight, as just to see if you're about it, right? Just sitting in the passenger seat. It'll change the way you look at physics. I know that's a bold claim, but it did for me, like truly.
Yeah. So I think that's the episode, Derek. Do you have anything to plug?
I got us to plug. Everything's a Spring podcast. We are back, baby. We're going to try to get on a more consistent schedule. Both of our lives are changing a lot, but that's just being in your 20s. Welcome to it. But things are looking pretty stable now. So I'd like to at least get an episode out every 2 weeks with the goal of us, moving towards back to our weekly. But, we're both adults that work and have families. So, yeah, no. Until you guys help us pay for it, it's going to be tough to cut one of the other things out, right?
Yeah, that's very true. And so I think, like, for me at least, the next few weeks should be pretty stable. And I'm looking forward to recording with you more frequently.
Sweet. And I'm so excited for the Airplane miniseries. Like, I have this is honestly embarrassing to admit. I have to listen to each one of these episodes like 3 or 4 times in just editing all of the versions of it, audio and video. And I think I've listened to the Boeing 247 episode like 3 times for fun. And that is an embarrassing thing to say because I'm literally just listening to my own voice and your voice.
That's fair.
For fun.
I don't think that's embarrassing. I mean, it is fun. And I think we put out a pretty good product. So.
Oh yeah. And like they're not all going to be hits, but some of them I think will come in handy. At least for me later. So I don't have anything to plug Whiskey Grill though. Because I heard
that's true.
I checked y'all's TikTok. Y'all are kind of cooking over there. Y'all got so many followers.
We are cooking on TikTok right now. So we're going live like pretty much every night, which is one of the reasons I'm having such a hard time recording over the past few weeks. Is because literally I've been going live for like 8 hours a day for the past basically 3 weeks.
You're kidding.
Not quite. Probably like between 3 and 6 hours a day, but still significant amount of time. Right now, we're really trying to drive sales. TikTok basically changed the algorithm on us in March, and everything went to shit. So we are now trying to figure out what TikTok wants us to do and how to get our Grail into the front of the right people. And I think we are starting to make some progress, and it is beginning to work. So that has basically been my life for the past 4 weeks. But so shout out to the Whiskey Grail. Find us on TikTok, Instagram, Facebook. We are a white oak drinking vessel for bourbon, scotch, or rye whiskey. It is a most excellent gift, especially with Father's Day coming up here soon. As you drink, the scent of the oak and the char mingles with the smell of the bourbon, and that helps smooth out some of the harshness of the whiskey and bring some of the more subtle flavors up to the front, making a much more pleasurable drinking experience. If you're interested, check us out. We have a whole bunch of video testimonials on our social media accounts, so you can really see what absolute strangers think of it, get an unbiased opinion on what differences the Whiskey Grail makes against drinking out of a glass. So check us out, www.whiskeygrail.com, @whiskeygrail on all of our social medias. And I appreciate the support that Whiskey Grail provides to Everything's a Spring.
I appreciate the great support that the Whiskey Grail gives to me. Like, anytime I'm sipping whiskey, I just feel so fancy, and it does really smooth it out. Like, I'm not just saying this because I'm your friend. Like, I'm the kind of friend I would tell you if it sucked. It kind of rocks. And every time I'm around Jim, he gives me another one because he knows I'm going to use them.
We're going to get them used.
So. We're going to get them used. I've gone through like 2, but that's my own fault.
Oh, yeah. And then allegedly this Friday or Saturday, we haven't quite figured it out yet, we're going to start drinking on the live.
Oh, you drinking on the live?
We're going to start drinking on the live.
Oh, I got to tune into that.
So we'll see how that goes. I'm going to get slammered because I have the alcohol tolerance of a fig.
And that's good. It's better to be a lightweight because, one, that means you don't have a problem with it just yet.
Dude, it's cheaper.
And you're a cheap date. Me and Jim go out to dinner, and if it's on me, it's just like get Jim 2 whiskey drinks or whiskey cocktails or something, or if they're feeling spicy, a Jarritos and vodka.
Just the one, and I'm done.
And I'm sitting there on drink number 3 like some guy's dad, Oh, this one's got a great mouthfeel.
I'm over. Just can't speak. So thank you guys so much for listening. If you enjoyed this episode, please give us a 5-star rating and review. It really helps us out. If you did not like the episode, please, reach out to us. Tell us what you think we could improve. We would love to make this a better podcast for you guys to listen to, and for us to create. So
we only get better when you talk to us.
We
and
only get
to
better when
all
you
of
talk
the
to us.
folks from My Favorite Murder who have jumped the ship a little bit and jumped on ours every now and then, welcome. And I see why you watch that podcast. It kind of rocks.
We'd love to have you stick around. I promise, not every episode is a huge nerd fest diving into physics and advanced avionics. So
I would say the first half of that sentence is false. Maybe not advanced avionics, but every single episode's a huge nerd fest. So go
that's okay.
Manage your expectations.
Not every episode is a huge, physics analysis fest.
Not yet.
Okay, fair enough. All right. Well, Derek, let's bounce.
Let's bounce.